All right, lecture number 1 of the semester is going to be climate change. We're going to be here for 5 to 6 of these short videos. Here's our main heading, and in our textbook, which is Open Geology / textbook, this is chapter 15, and today's material is 15.2 specifically and 15.3. What I want to do in today's lecture is strip away emotion, strip away bias, strip away predictions. We're going to do that stuff later. And we're going to get into definitions and direct observations for these next 15 minutes or so. Feel free to watch this on 1.5x if you want to speed it up. Now, we did poll the class before starting climate change to get some of that emotional response. I think this is a very interesting context. We've got a lot of nervous students this semester, not very many skepticals. That's opposed to 2 years ago, where I had actually 15 people who were skeptical of climate change. It's interesting to watch these number change over the years. So we're going to go through definitions, and the very first definition I would like to do is going to be a definition of climate versus weather. And it's a big deal. This is maybe, I don't know if this is the most important definition of the day, but what I want you to know is that climate refers to the range in weather conditions over decades for a specific region, whereas weather is the short-term precipitation, temperature. So for note-taking here, it's you can write more if you want to, but I want you to have short-term written down in your best penmanship, which I promise you I'm trying to do. And you could put like T here for temperature, comma, precipitation. It's a short-term thing. That's the most important part of this. Whereas climate is going to refer to a full range in weather. So it's a range in temperature, it's a range in pressure over decades for a region. Now, we are maybe too young to understand climate fully, but I want you to think about this as like climate is like the running average over half of a human lifetime. So maybe a grandparent could look back and say, oh, back in my day, climate has changed, because they have a record that's long enough, because the key here is going to be decades. So those are our first two definitions. Definition number 3 is going to be climate change. This isn't meant to be complicated, and in some ways this is dull, but climate change is going to be a long-term change for a region. What about global warming? This is a bit more of a loaded term. Climate change is culturally approved. It is more technically correct. It has data to back it up, where global warming has been more alarmist. Now, it actually might be true, but it has been controversial and it is less technical. And so global warming, it refers to the change in surface temperature, all right, measured at the surface of the earth, not ocean or not high up in the atmosphere, relative to some baseline. And that baseline tends to be chosen at around 1850, which is during the industrial era, when we had enough thermometers to really get an accurate reading. So relative to baseline. 1850 is generally our number. Next definition is going to be greenhouse gas. These are all the terms that I need to use freely over the next lectures. Greenhouse gas. So that's why we're getting the definitions out of the way right now. What I like about the term greenhouse gas is that I want you to picture a true greenhouse. How does a greenhouse work? You grow plants inside of a greenhouse. Here's our greenhouse. It's made of glass walls, and what these glass walls allow is that incoming radiation in the form of light is able to come and hit our plant. I'm not going to change to green ink. And that it doesn't allow heat, which is long wave radiation. My drawing's bad. There it is. There's our long wave radiation to escape, and so it stays within the greenhouse. And that's what these greenhouse gases are. There's going to be 3 of them. Our technical definition will be, these are gases that absorb long wave radiation radiation. And when I say long wave radiation, I want you to think heat. But they transmit short wave. And our transmission of our short wave, this is transmission of light. So transmit short wave radiation. Okay, this is light. We have a number of different greenhouse gases, but there's three big ones. Our three big ones are H2O, CO2, and methane, which is CH4. We can even draw these. For H2O, you put an H in the middle, and you go down, and this is purposefully lopsided. It's a polar molecule. CO2 is not a polar molecule, so for CO2, you have one C with two O's, and this is a straight line. CH4, you put a C in the middle, and H goes up. Oh boy, that's a sloppy H. And you have 1, 2, and 3 H's that come off the base of this form that's a tetrahedron. All right, those are our three greenhouse gases. Now the last definition we're gonna go for today, we'll put it here at the bottom of the page, is anthropogenic. Did I say that right? Anthropogenic. And that means man-made. All right, this is going to be a human influence. Oh, what is happening here? Excuse that mistake. All right, let's try again. It's human influence is main cause. Right, this is where some of the controversy and the discussion and the science is happening is, okay, if climate is changing, is it an anthropogenic effect? Are we doing it as humankind? Those are our definitions. Now I want to go through some observations. Within these observations, I will try to anchor them with some graphs and figures so you believe it. And we'll see how, okay, we just did our definitions, and now our next part is gonna be observations. I'm gonna give you 10 observations. In actual lecture, we go through more, but I think 10 is more than enough. These are observations, scientifically kind of documented things. One of the things that has been observed is that air temperature has risen. Air temp risen since we've been recording it by about 1 degree C. Now this is not true for every place on planet Earth, but in a lot of places on planet Earth, this is true. So in this graph here, we can see the temperature of North America has increased since 1850. Northern Europe, true. South America, Africa, a lot of different places. Interestingly enough, it's not true for Texas, where we live. The temperature has been about the same since all of recorded time. Now, just like air temperature has increased, ocean temperatures have also increased. Ocean temp has risen similarly by about 1 degree C. Another observation we have is that ice is melting. This is a very easy one to observe because we see glaciers and ice sheets are reducing in their volume and melting away and putting water into the ocean. I've got graphs to show you each of these. So for ocean temperature rising, here we are since the start of recorded, and we see that increase of ocean temperature. What about ice sheets melting? We could show this in individual pictures in some mountain range or going to Antarctica or Greenland, and what we see here is that the mass of ice, all right, anytime I show you a graph, I want you to look at the x-axis and the y-axis. So the x-axis here is time going towards today, and here's the mass of ice and both of these ice sheets on our poles that is decreasing through time. All right, I'm not rushing, I'm just trying to be efficient. Number 4. Nope. Oh no, I did it again. Mistakes happen. I'm going to get better though as this semester goes on. All right, so let's go down to number 4. Our fourth observation is that sea level is rising. Sea level is rising, and it's rising by a fairly large number of approximately 3 millimeters per year. That's pretty fast. What is there? There's 1,000 millimeters in a meter. A meter is 3 feet. So this is a noticeable effect, and that's why we're starting to see coastal areas and start to flood. So here's our graph of sea level change. I'm kind of flooding you with graphs today, but these are direct observations where sea level has been increasing, and it's a very steady increase. Well, I bet it has to do with ice sheets melting, because where does that ice go? It turns into water, it goes into the oceans. When a material heats up, it tends to expand. That's true for water, so if the ocean temperature is rising, that means the ocean volume is expanding, which can create a sea level rise. Some of these effects compound each other and influence each other. All right, observation number 5, more extreme events. So this means like we're seeing that storms are getting worse and droughts are getting droughtier. I don't have a graph for you here, but you've probably heard about this. Here's a rain cloud. Here's a big tornado coming out of that. You know, maybe we've got a farmer's house right here. We got lightning bolts. Anyways, we're just trying to show here that extreme events are becoming probably more common, and they are getting more severe in themselves, so leading to more flooding and more destruction. Climate zone shift is a really interesting observation. Climate zones shift. And what this can mean is maybe you have something like a mountain range, and there's a tree that used to be alive on the lower slopes. But because of climate change, now that tree is more comfortable and the population lives higher up on the mountain. This is true for things like cherry blossoms in Japan. We know that cherries become in season later in the year than they used to. We know animals have started to migrate towards higher elevations. All right, we're more than halfway done now. Number 7, it's our 7th observation, and that is that CO2 is rising. What this means is we can measure the amount of CO2 in our atmosphere. In general, it's at around, right now, at around 420 ppm CO2 today. And in a later lecture, I'll show you that specifically. But when you were born, it was closer to 400 or 380. When I was born, it was in the 300s. When your grandparents were born, it was in the lower 300s. And so in terms of, you could even draw this graph. This is CO2 concentration, and this is time. Over your lifetime, this is the graph. There's an interesting seasonality to it, which is why I'm drawing it zigzag, and we're going to talk about this in a later class. Now, those are modern observations of climate change, but we could also look deep into the distance past using geology with a concept that's called paleoclimate. Paleoclimate is fascinating because the rock record preserves evidence of past climate. I'm going to give you 3 of them here. There could be 100 of these because there's been so much geologic research on how climate has changed in the past. This means it is not anthropogenic, right? I don't know, I'll put a human here. All right, this is, the paleoclimate things are not anthropogenic. It is part of the natural cyclicity. And these things are, you imagine like ice ages. And we've had Little Ice Age. The Little Ice Age is not as famous as the major ice ages. The major ice ages, we call them the Pleistocene ice ages. There's geologic record for both of these things. The Little Ice Age, there is human evidence because this occurred from around 1300 to 1850 AD. And there's stories of wars where armies were able to cross small seas or rivers and attack. Or there's a lot more people were trying to figure out why there was so much more cold and all the famine and all the sadness associated with this, and so they tried to kill witches. For my humanities people, you've maybe heard of the Stradivarius violin. It has some amazing tone and they're worth millions of dollars. Well, Stradivarius was making his violins during this Little Ice Age, and they think that the wood he was using was so dense because it was a cold period of time. Now the Pleistocene ice ages, these are the big ones, the woolly mammoths, the things that the TV shows and movies, right, the cartoons have been made about, and this was a time period when the ice covered large portions of the northern and southern hemisphere. Now the Pleistocene ice ages, the Pleistocene is an era from 2.5 million years ago to today. The ice ages would happen and then retreat, and the ice would come back and then retreat and come back and retreat every, maybe let's call that 15 100,000 years. And so this is certainly climate. It's not weather, it's long term, it's over decades, it's over thousands of years, and it was natural cyclicity, natural change. All right, we're almost done with today's lecture. We better be. I got just 2 more examples, 2 more pictures. Well, during the Cretaceous, during the time period of the dinosaurs, climate was hotter and wetter than it is today. So here's a picture I snagged from Big Bend National Park, and what we see here is just humid tropical landscape. But what I want you to picture is that the average world temperature was here we go. Yep, there we go. 5 to 10 C hotter, and the ocean sea levels were like 50 to 100 meters. Oh boy, that's bad sloppy. That says 50 to 100 meter sea level higher, because temperatures were so much higher and there was essentially no ice on the poles. And then our last example, we'll wrap up class here today, of our definitions and our direct observations. This is snowball Earth. Snowball Earth is a really cool concept, and the idea is that at one time in Earth's history, we were a slush ball, a snowball, where the entire planet was ice. Here's a picture. This is just an icy moon. I believe this is Enceladus, but you could actually picture that Earth used to look like this. And it was a period of around 650 million years ago where geologists have found glacier deposits at the equator. And by the concept of uniformitarianism, which I taught you last time, if the glacier deposits are at the tropics, then the present key of the past, we could then assume that if glacier deposits are at the equator, then glaciers are at the equator. If glaciers are at the equator, then the whole planet was an ice ball. This is showing evidence for climate change. All right, thanks for sticking with me today. See you next time.